Welcome to this video lecture on the Clausius inequality. The Clausius inequality is used in the derivation of, or at least the definition of, entropy. So this will be a short video lecture just to introduce the Clausius inequality, what it is. But really it's a tool used to define entropy, which we'll do in the next video lecture. Go ahead and take a look at your screen. What you'll see here is a computational fluid dynamics simulation, or CFD simulation, of what appears to be flow through a centrifugal impeller. Centrifugal impellers are used in pumps or in compressors, and the idea is that fluid would come in from this direction, and then this impeller rotates around, and the fluid gets thrown between these blades out towards the edge here. And what you're seeing in this particular plot is that the colors correspond to entropy. Down here it's a little hard to see, but it says entropy. Honestly, I'm not sure whether it's entropy or entropy production. I sort of suspect it's entropy production, which is a term you'll hear about later today. But red values correspond to large entropy, or like I said, I think this might be entropy production instead. And blue is a small value. And so what you can see from the simulation is regions where you have a large production of entropy, like right at these tips of the impeller vanes. And so this is, as you'll see later, entropy production. When you have large entropy production, what that means is that you have a lot of irreversibility occurring. So that's typically undesirable. You generally want reversible operation that gives you the highest efficiency. So when you produce a lot of entropy, that means you've got some inefficiency there. So these kinds of simulations can give you some insight as to where you're producing a lot of inefficiency or irreversibility, and then you can change the design or operating conditions to see how you might improve it. So I just thought that was kind of an interesting example of a thermofluid system that's using some of the concepts that we're talking about. Okay, so let's get into the Clausius inequality. So I'm just going to show you what the inequality is. I'm not going to do the derivation here. If you're interested in the derivation, your textbook has it. I also have a derivation in my book style notes, so we won't go through it here in the lecture. But the Clausius inequality is given right here. What it says is that the integral over the boundary, the b here means over the entire boundary, so the whole surface of a control volume or the whole surface of the system. If you do the integral of the heat transfer into the system divided by the absolute temperature where that heat transfer is occurring, and that you do that over a cycle, that must be less than or equal to 0. And the derivation of this relies on the second law, the Kelvin-Planck statement of the second law of thermodynamics. So this inequality comes about from the second law. Okay, so the derivation relies on the second law. Again, the b refers to the integral over the system boundary surface area. So if I have, let's say this is what our system looks like, or control volume, this surface here is my boundary. Okay, it's the control surface, or the boundary. And when I say that we have this heat transfer divided by the absolute temperature of where the heat transfer is occurring, so let's imagine we have just some small piece of the boundary here, and there's some heat transfer coming through it. This would be the absolute temperature at that particular location. So you would take the heat transfer here divided by the absolute temperature at that location, and it's an absolute temperature. It's not a degrees Celsius or degrees Fahrenheit. It has to be Kelvin or degrees Rankine. And then when I say you integrate over the boundary, that means that maybe there are several places you have heat transfer coming in and different temperatures. So this could be like 1, and this could be 2, and maybe you have a third one here. Call that 3, so on and so forth. You do that over the entire boundary surface, and that's that integral. And you do that over the cycle. So this is operating over a cycle, so that's why we have that subscript. And when you sum all those together, they have to be less than or equal to 0. The equal sign holds for an internally reversible process, and then the less than sign occurs when you have internal irreversibilities. Okay? So that's the Clausius inequality. We often write it in a different way, and this is kind of leading us into a thing known as the entropy equation. We can take this expression, and instead of making the inequality on this side, let's just use an equality and put a quantity here called sigma cycle. This is called the entropy production or it's known as the entropy generation term. So we're now starting to get this word entropy showing up. We'll formally define entropy in the next video lecture. Okay. This is not entropy, this is entropy production. They're different. Entropy is a property, entropy production is not. But we'll cover that in the next video lecture. So if we define, if we do our Clausius inequality in this form rather than this one, what that means is if you have an internally irreversible cycle, then that entropy production term has to be positive. So if it's positive, when we throw the negative and sign in front of it, it makes it less than 0, so it corresponds to that less than sign. And then if it's internally reversible, then the entropy production is 0, and so this will be equal to 0, which is the same as the equality sign up here. Okay, so that's how we do this. And the other thing that we'll add to it is if it's impossible to have a negative entropy production. Okay, that's impossible. The reason for that is if you go through the derivation, what you'd find is it means that you're violating the second law of thermodynamics. So you can't do that. It always, this entropy production has to be greater than or equal to 0 at all times. Okay. So this gives us actually a way to determine whether a certain process or a certain cycle is possible or not. Okay, if you get a negative entropy production, then you know it's impossible. You can't possibly do it. It always has to be greater than 0 for any real process and equal to 0 if it's idealized, meaning internally reversible. Now, this is one way to write the Clausius inequality. You can also take the time derivative of this equation. So if I took the time derivative of it, instead of the heat transfer, we'd have the rate of heat transfer, which is indicated by the Q dot, and then instead of the entropy production, we'd have the rate of entropy production or the rate of entropy generation. Okay, so that's just another way to write it. Okay, that's really all I wanted to say about what the Clausius inequality is. Again, if you want to see the derivation, take a look at the book style notes or your textbook. It's not that hard of a derivation. It's just something I don't want to cover here. But the real power in using the Clausius inequality is in the definition of entropy, which is going to be in the next video lecture. So we'll just go ahead and end it there.